Well, thank you for all showing up here after lunch. I know it's the last day. It's great to see such an audience. It's been really exciting to be here in Montreal. I've always wanted to visit, and this is my first time. So thanks, Recon. It's been a great conference. So what I'm going to talk about is reverse engineering on OS X. In particular, kind of how we started with Dtrace and then what mess we've got ourselves into. So this work is done by myself and David Weston. He couldn't make the trip, unfortunately. He totally pussed out and made excuses about moving or something. So here I am, swinging the whole deal. So Dtrace is a tool that was created by a couple of engineers, about 3 of them, back in 2001, I think, and was publicly put into Solaris 10 and open sourced under the Sun's SDDL license. And then recently, and Leopard, OS X picked it up, and they ported it to their operating system. There's been other adoptions, too. QNX has a partial implementation. And then just last week, this guy, John Birol, I think I'm pronouncing that right, committed a Dtrace port to FreeBSD current, so you should be seeing that in 8. So we might also see versions in OpenBSD and other BSD systems. Linux has kind of done something different because they don't get along at all with the SDDL license. So they've created System Tap, which is intended to clone Dtrace, except kind of lacks application tracing, user land tracing, which is, of course, what we want to do a lot of. And interestingly, the FreeBSD port was initially sponsored by Cisco, who pulled support, and then it was picked up, I think, by Yahoo and Juniper, so extra juice on that stuff. So Dtrace is really used as sort of a performance monitoring framework, right? So it gives you the ability to instrument all your applications or instrument library calls, instrument the kernel, and make measurements or observations about what's going on in memory space, with parameters, or with timing. So the way it works is that we define probes that get triggered during runtime. So this is all very dynamic, right? We're not talking about static analysis. So what we have here at the bottom is sort of logical categories of probe types. And this is where you're going to specify a probe is a PID probe, meaning it's going to trace the application, or it's a kernel probe, or it's some sort of I/O probe. This all exists in the kernel, right? So Dtrace is heavily involved with the kernel. It's built into it. And then there's a userland library called libdtrace that we can interface with. So we write these little Dtrace scripts, which will utilize libdtrace. There's also a number of other tools on here that utilize libdtrace. So things you're used to seeing in Linux, like ptrace, no longer exist in OS X. Instead, you have everything implementing something that interfaces with libdtrace, so like truss or something. So this is what we're really interested in here in the beginning, is writing Dtrace scripts that allow us to analyze our applications that we're interested in reverse engineering. So first, about the language. Dtrace is said to be a subset of C, except that that's kind of a joke because it just happens to follow the same syntax. There's not actually loops or conditional statements. So what kind of language is that, right? We can't do much useful. But there's good reasons for that. Like if you're going to instrument something, if you're going to hook code in the kernel, and you accidentally screw up and you have an infinite loop, what's going to happen? Your kernel's never going to get control back, and you're just gone, right? You got to reboot. So there's reasons that they limit the language. If you've ever seen awk, the structure of a D looks a lot like that, where you have a condition, like a conditional statement that has to be evaluated, and then some block of other statements that happen after that. So people use this a lot for performance monitoring, right? Measuring I/O, understanding information leaks, stuff like that. Another cool part about Dtrace is they built it so that like a Sun engineer can code some Dtrace script, go into a customer site, and analyze a production system without having to restart the processes, take anything down, or have any effect on the production operation of the system at all. So before you instrument anything with Dtrace, there's no performance hit. And when you're doing the instrumentation, there's a small performance hit. So that's a goal, a design goal, right? Another design goal was to not affect the application. So this is different than like rewriting function pointers so that you can hook the code, because Dtrace is actually providing that framework in the kernel, kind of like when we saw that device driver, I think, was it Jason, that presented where he's grabbing code from kernel land by hooking things like uname and system calls. This is similar, except it's built in the operating system itself. In that sense, since it provides a framework for hooking, it's almost like a friendly rootkit, right? We don't have to bother with overwriting pointers. We just specify these probes. So you'll see many of these things, Dtrace, Ptrace, Truss, and Ptrace using Dtrace and OSX. And there's a million different things you can do, right, with a tracing framework like this. So Dtrace provides you the framework to implement those million things. The real takeaway here is that Dtrace combines system performance, statistics, debugging information, execution analysis into one tight package. So then we get to figure out, okay, how do we take that debugging tool and use it for reverse engineering? There's a ton of stuff out there that's already been done. For instance, hooking I/O to watch all the I/O that applications do. You can hook the keyboard to log keystrokes, cute stuff like that. Here's a quick example that shows a Dtrace script counting the number of syscalls that different applications are making. So this is system-wide, right? We're tracing every possible application on the system at once. And every time we see a syscall entry, we record the name of it and count the number of times. So here we can see VMware is doing a lot of syscalls. You'd expect that. What you might do next is zoom in on VMware and say, what syscalls is it making? So basically redo this, but only with tracing VMware. Here's another file open Snoop, right? So we run this little script, and we can see all the files that are being opened and by which applications. So you'll see something like this. Here's the application. VMware is opening dev urandom. iChat's opening some PDES preferences files, and so on. So good for investigation. So we've got probes, we've got providers, we've got predicates and actions. I'm not going to go over this too much. You can read the docs. The syntax looks a lot like this, pretty straightforward. The probe specifies the point of instrumentation. The predicate is some conditional on which to fire that probe, and the actions are what you want to have happen when that condition is true. Usually this is just recording data. Okay, so this is the good part, right? How do we use this for reverse engineering? Well, it turns out to be extremely versatile, right? You really do need a good tracer. We can see how applications interact with the rest of the system or with each other. It really provides us with kind of a tool to help with rapid development of reverse engineering tasks. One of the interesting parts about it is it doesn't really attach to the process because it's designed to be non-interfering. It doesn't set breakpoints in the application. So we get a lot of useful things, like people will go implement tracing tools themselves because they need the tracing ability, and they're on an OS that doesn't have something like that. And they have to deal with all these things, like how are we going to do symbol resolution, and now I have to write a function that's going to print the CPU state, and I want to print something that parses the stack and prints a backtrace. So Dtrace provides a lot of that to us. So for instance, here's a quick show of the control flow of ADM, right? So you can see which functions are calling which functions and when they return. Here's a simple stack trace printed when we enter strcopy from FTP. We get symbol resolution. We also get the offsets within each function, so we can open up stuff in IDA and see the exact instruction that's being executed. We can also print function parameters, right? So this is really interesting when you want to see what is being passed to some function that you found out is vulnerable or crashing. You can also change values in memory with the copy out if you enable destructive actions. You get CPU state, right? You can easily print out all your registers, EIP, EAX. stack pointer, stuff like that. Here's another example of a destructive action, right? Here, we're hooking the entry point. We record where we are, where the argument is that will be returned. Then we hook the return point for uname, the system call, which is supposed to return the system's kernel information. And then we can modify it how we want, right? So we've got Windows running on a PowerPC, 2010, et cetera. So anytime any application then calls the uname syscall, that's what it's going to get back. Another example of snooping, right? So this is going to record everything that any application prints out to the terminal. So this is how you can snoop on another user's shell. So hopefully this sparks a lot of ideas with you guys about things you can use this for, just for fun. Things we're thinking about is like monitoring the stack, right, for detecting stack smashes, heap smashes, doing code coverage, integrating that with IDA. We haven't implemented fuzzer feedback yet, but you could do smart fuzzing where you're tracing inputs to certain functions that you're trying to fuzz as you're fuzzing it. So it's important not to think of Dtrace as a debugger, right? Because it's actually totally different. It's a tracer. So these are two separate tools, a debugger and a tracer. And you really need both of them. Tracing really provides you with a dynamic monitoring of the application at runtime. One of the really cool things about Dtrace is you can trace kernel space at the same time. So if you want to see, if you're troubleshooting a kernel bug, you can see where you transfer from user space into kernel space, and then what's happening in kernel space in terms of parameters and stuff. Of course, it gets tricky if your kernel crashes, right? Because then you can't do anything about that. So I got a section on kernel debugging later. So that's one point, is that Dtrace doesn't do exception handling at all because it doesn't want to interfere or change behavior of the application. So that's something that we wanted to do and had to do differently with our own debugger. But what you can do is like trace to a specific spot in execution and under a certain condition, stop the application and then attach a debugger and continue on with doing whatever you want, like just attach GDB. There's an interesting part about Apple not wanting you to trace certain applications, and you can imagine why, right? They have this whole digital rights management thing with iTunes. They don't want you just checking out what's going on in memory there. So they prevent GDB and Dtrace from tracing things like iTunes by using PT attach deny. So I'll talk about that later. It was actually discovered in a really interesting way by someone who was tracing stuff and going, where are all my probes going? So there's a bunch of other tracers out there too, right? Tross, Ltrace, but they have a more limited scope. And Dtrace is really a framework for implementing your own tracers. There's things like Valgrind. Ptrace is totally broken on OS X. There's Vtrace as well. But there's, again, some limitations that we already touched on. The language is very limited. So you can't do loops, right? And that's, of course, what we want is implementing control structures. Also, you can't modify registers, right? That would be really helpful for us. You can modify memory, but not the registers themselves. So that's the kind of thing you want to do when you're stepping EIP back one, so that you can, run a breakpoint or run an instruction at a breakpoint that you set. So there's some other issues to be aware of, right? Dtrace is for performance, so if you instrument too many probes, it'll just drop probes, and it'll tell you that. So you need to tune in scope so that you're not instrumenting too much. There's also performance options like buffer sizes and buffer swapping rates, which you can tune to make sure that you don't drop these probes. There's also the issues with exception handling. So this is where Redbug, as we call it, comes in, right? So first we're going to touch on retrace, which we wrote kind of a wrap around Dtrace with Ruby. So we did this because we wanted loops, we wanted object-oriented programming structures. We wanted to have be able to interface with other Ruby libraries out there, like the Metasploit project, MetaASM, IDA-Rub. So what was I looking at? There's this library, Ruby Dtrace, that's written by Chris Andrews that allows you to call call Dtrace from within Ruby. So that's what we're utilizing. There's also IDA which was presented at the last Recon, which lets Ruby interface with IDA over the network. So this is key in a lot of our examples, is that we have IDA running on a Windows system with the IDA plugin, and then we have Ruby running on the OS X system with Dtrace tracing. So that way we can trace stuff and communicate back and forth with IDA. So we found that we can quickly shorten the time it takes to track down bugs and pinpoint vulnerabilities. So we were presenting this once before at another conference, and some guys came to us and said, hey, we found this iPhoto bug, and but we're stuck. And so over a couple of beers at the bar, we just sat down with them and said, okay, here's what you can do. You want to trace through so many printfs until you hit this exact one, and then that's when you want to start analyzing the stack. So that was a fun time. Another cool part we can do is trace instructions and then graph code coverage in IDA. So this will show us which basic blocks we're hitting. And so then we know what we're not interested in. We can also do it the other way around, right? So you trace the application and you monitor for all, like, you use the application normally and it generates all this code you're not interested in. And then you trace the application and cause the overflow, and then you know the delta, right? All this boring stuff happened, we don't care about that. All the boring stuff happened with some extra things, and then you can do the delta and figure out what code parts you're actually interested in. So Redbug picks up where Retrace left off. So it's a programmatic debugger for the mock API on OS X. It partially exists in some forms already, right? Charlie Miller did a PyDGB port to make PyMate run on OS X, so he could do like file fuzzer parsing. So what he did there was like write a MacDL file that translates everything that PyMate needs into the mock debugging API equivalents. But it's not complete in the sense of what everything we want to do is. So we're re-implementing it. So you can expect to see something like Nox GDB, right? A programmatic Python debugger, where you set breakpoints, you can change memory values. So this is our plan, right? We use retrace and dtrace for tracing, IDA to interface with the disassembler. You could also use something like meta ASM, and then Redbug is our debugger. So where we're at now is implementing C code that wraps around the mock API, and then use Ruby bindings to bind those C functions to Ruby. Then we'll create a higher level Ruby class that allows you to easily create processes, attach, set breakpoints, specify handlers for breakpoints, walk memory structures, change permissions on memory segments so that you can modify them, and also query information from a disassembler like IDA. So for example, if we consider this iPhoto bug format, right, it's a URL handler bug where you put in some characters and it crashes. So what we want to do is trace through the code until we see a specific invocation of printf. And then we want to pause the application there and attach our debugger. Then we want to do some analysis with something from the disassembly information and maybe set some breakpoints or overwrite some memory or look at values in memory. So the code should look something like this. First, we set up our Ruby Dtrace script, and then we just attach to the process and run it. So that gets us down to here. Once this hits this spot in memory, it's going to stop, and it'll stop the application. So then we'll have control here. We can connect to our IDA rube, figure out where we are in memory, and then get the disassembly information, right? Look for the return instruction, attach our debugger, set the breakpoint there, and then continue until we hit it. Once we hit that breakpoint, we can inspect our memory registers. We can look at the memory we tried to overflow, make sure that the value we thought was there is actually correct. So that's the kind of thing we hope to do with a programmatic debugger. Also, there's something funky about Apple's ASLR implementation. like not everything's random, and it's not clear when things change or get re-randomized. So it'd be cool if we could, load up an application and do a bunch of symbol resolution to find out where all the addresses of certain functions are, or certain libraries. And then search through memory to see, can we find a value somewhere that references that function or that library, or some value that's relative to that library. And then rerun the application again, checking that same address, and see if we can ever find an address in memory that's static, that's always at the same spot, and has a value that's always relative to that library. And in that way, we could be able to locate libraries at runtime based off this static address. So that kind of analysis we hope to be able to do with debug. Unfortunately, it's not out yet. I really wanted to have it done. We've been working on it all week, but we need to do some more testing. So we're thinking probably in another week. So if it's not out by then, just bug us, send us email. Okay, so let me make this all concrete by showing you an example. What we're going to do is trace the stack until we find an overflow. When we detect the overflow, we'll print all the information that's useful to us. So imagine that we fuzzed our application, and now we need to pinpoint the vulnerability. The easiest example, right, is this. Trace all function entries in our application. If EIP is ever 414141, we know we had our overflow. So stop the application, and then we do our analysis, right? Okay, this is trivial. This actually isn't really useful, though. We want something much more generic, something that works in all overflow cases. So it's kind of obvious what to do here, right? We've all seen stack monitors before. You record the return address that's put on the stack. When you exit the function, you check that value. If it's different, you know something funky happened. If it's the same, everything's good. That's simple enough, but you have to understand how Dtrace works with tail call optimizations, because sometimes the compiler will say, hey, I don't actually need to create a new stack frame on the stack, because what's being returned from this function is it will not be processed after the next function. So I can explain that later if you want to come afterwards, but tail calls they're just tricky in terms of how you trace them. Like, is it considered a new function entry or not? Because it's a new function, but it's not a new stack frame. There's also problems with functions without return probes, and you have to deal with those. So our first approach didn't work. We went back and redid it. I won't go over the details of tail calls because it's actually extremely boring, but if you're excited about it, please talk to me afterwards. So our new approach is really to store the return address when we enter a function in an array, and then once we leave that function, we compare the return address. We read that same memory segment and compare. If they're not different, we know that some overflow happened. Now, how to deal with the missing probes is simply not to trace them, right? Dtrace gets tripped up by things like jump tables and other certain functions that just don't have return probes because they couldn't figure out how to properly implement it. These are usually functions that you're not interested in, so you can just exclude them from the trace. There's ways to detect which functions which don't have returns. You can simply print out all the traceable functions, see their entry points, and then figure out which ones don't have return points. You can do that with a -l flag on Dtrace. You can also run the application and count all the places where functions entered, and then record all the places where they exited, and just note the delta. Then you exclude them with some predicate like at the bottom there. If the probe function is not equal to everybody jump, then don't trace it. So, okay, enough talking. Let me show you a demo. So here I'm going to start a public QuickTime RTSP exploit, right? There's a ton of these. This is a server, so I'll open up QuickTime and connect to it. So what I'm going to do is visit the malicious URL, right? Get pwned, and then watch my stack trace monitor detect it. So I just note the PID. I'm going to go ahead and launch retrace and attach to this process. So here's our menu. You can see some stuff in here like search memory, attach debuggers. This is already up. So you can have access to this, no problem. It's on pophotret.org or, well, that's the only place it's at right now. So we just launched our monitor stack script. Now go visit the malicious URL. So in the background, you can see everything printed out. Now this is halted because retrace stopped the application when it detected the overflow. So we get our message about overflow being detected. And then here's all the useful information, right? We get the module name. It was in the QuickTime streaming library, function name, our expected return value and what it actually was. And then we print out the CPU context. You can see a number of these are overflowed. So pretty big stack smash there. We also get a handy call trace, which has all the instruction, or the addresses, the libraries, functions, offsets. And then we just stop the process. So from there, we can attach our debugger and continue on doing our analysis to figure out what happened, or if you're just trying to use this defensively, you can kill your application. So there's some other fun stuff we can do. We can actually trace every instruction in an application. That'll allow us to do block-level coverage. We can't do things like trace block entry points only, though. I already mentioned some of this stuff. One of the coolest parts is conditional tracing based on function parameters. That turns out to be really handy. So let's talk about that. This is actually pretty simple, right? We just write a Dtrace script that traces every instruction in the application. That can be like pretty thorough. You kind of usually want to do all the instructions in one library or something like that. It can trace application, or it can like highlight what's being run in IDA in real time through the IDA Rube connector if you can catch up, if you can keep up with that. Here's the Dtrace script for the process. Trace in the main module, trace all functions and all instructions. Print out EIP. So that's all Dtrace does, and then the Ruby trace, the retrace part of it, parses all those EIPs and then changes the color of them in IDA. Now, there's some things to be aware of, right? If you're tracing a library at runtime, the offsets are different than when you load that binary in IDA, so you have to deal with that mapping, which is easy. A VM map will tell you what the address, where the libraries are loaded at runtime. So this allows us to fuzz our application and then see what code we didn't hit and try and inspect to understand how we do get to that spot in code. We can also visualize code paths real easily, and this is the real takeaway there. So as Craig said, every presentation needs an IDA screenshot. This is a function, the full function. All the red blocks are code that actually got executed during the run. So at runtime, we can see what code we're interested in and what code that never got run. So that's pretty handy. This all works now. You can also do graphing of dynamic call traces, right? So similar to, I have to get that application that, I forgot his name already, Gara had, because his graph was way cooler. But this shows tracing at runtime, so we can see which functions call which other functions. So if you know there's a vulnerability here, and they patched it, but you notice from diffing the binary that they changed only this, you might be interested in seeing how can I get here to still reach that vulnerability from some other code path. All right, so stack is kind of trivial, right? Let's talk about monitoring the heap because that's where all the fun stuff happens. This is now sort of turning into a major attack vector for exploits today. There's a lot of cool work that's been done on heap exploits already. Defensive mechanisms are being put in place to make the trivial heap exploits really difficult, right? So we can't just do standard unlink exploits anymore. There's some good papers explaining these topics and kind of justifying that by Dave Eitel and Wiseman. I think it's Nicholas Wiseman on their presentation site. So this is a new breed of attack, which really requires us to understand what's going on with heap allocation. So of course, with dtrace, we can just hook malloc and see what's going on there, hook string copy, and make the association so that when we do see mallocs, we can wait until we see that that memory actually being used, and then make sure it's being used in an appropriate way, or check if it's being overflown. So, for instance, we can hook the malloc functions in OSX. There's actually a bunch of different ones, right? And we can find out something like this, where malloc's it's all being, these are sizes, right? So each malloc at this address is mallocing a memory space this large, or this large, or this large. That's because on OSX, there's actually 4 different heaps of different sizes. So depending on what size of you malloc, you get memory space in a separate heap. So there's like a tiny heap, right, small heap, large heap, and huge heaps. So we have to deal with monitoring all of these. So I'm skipping ahead. I already mentioned this. There's 4 heaps to monitor. So we hook our standard memory copy functions, right? And we hook allocs, and we make sure they're appropriately used. So let me skip to the video. So in this case, we're going to trace a browser. We'll go through a trivial example, and then we'll trace the browser. So this is your typical bad C program, right? You've got your buffer, you've got your bad usage here. So we're going to make sure that we can detect this with our heap smasher. Now, we're also running IDA at the same time so that we can relate what's going on with the overflow to the disassembly code. So this is our program text, right? You see the string copy in there. We're going to start up our IDA Rube server. So now we'll run our heap smash detector, launching this application with some bad input. So this is going to tell us not only where the crash happened, but also where did the malloc happen that was eventually abused, what the sizes were. The destination address was 16. The actual copy size was 30. Okay, we know what we have to play with. Also, when it was detected, it was also marked in IDA. So we said, okay, this is the instruction where it happens. It's kind of hard to read that, but it says all the same information in here. Heap overflow probe, PID, it specifies the probe, and then the addresses and the size and everything. So same stuff gets marked in your code. So you can imagine fuzzing your application, having IDA hooked up to it, and then getting a bunch of these in different locations, and then later going back and analyzing them. So there's a lot more we could do with this, like visualizing the heap space, or trying to monitor heap allocation algorithms and understand them so that we can create tools like Alexander Sotorov's heaplib, which does this really cool heap feng shui thing. So if you're not familiar with that work, he's figured out how to, from the browser within JavaScript, make allocations of strings or call string concatenation functions that actually translate into process level heap allocations. So in a lot of systems, like where you have a JavaScript library, it has its own heap. So you're interested in in what situations does creating this object create malloc space in the custom heap versus when does it malloc space in the process heap? And is there a way that, can I pinpoint the situation in which it's always mallocing space in the process heap? Because then I can do things like heap spraying or more accurately, heap feng shui, where I can construct and control the layout of the heap. So that's what you really want to be able to do, and that's where tracing this stuff can really come in. We imagine that you guys all have a lot of great ideas about how to use this stuff as well, maybe for garbage collection tracing, so you can understand when things are freed and not. And maybe there's a class of attacks there. Okay, I'm going to skip this section, right? Using Dtrace defensively, this is kind of not the context of Recon, but there's this paper where they say, okay, you can fingerprint your application by recording the syscalls it makes. And then if it ever makes a syscall that's not within that fingerprint, something must have gone wrong. So if, for instance, if QuickTime ever starts changing your DNS settings or calling bin bash, maybe you know something's gone wrong, right? So you can write quick Dtrace scripts that will check that, make sure that it doesn't ever call, that it never execs bin bash. And if it does, you can stop it. Also worth mentioning is Tracing Rootkits. There's a paper out there on the Sinar rootkit about how to avoid being traced with Dtrace. It's actually easy, right, because Apple implements this whole PT attached and I thing. So you can just set that in your rootkit code, and then Dtrace won't be able to trace you. But there's also a kernel module, which, of course, came out the day after that announcement that allows you to trace things like iTunes. So this is an interesting area, but actually it's kind of easy to trip up Dtrace because it's really sensitive, and its goal isn't to do malware analysis. Its goal is to do production-level tracing and not interfere with the application. So, you just use a bunch of function pointers, and you can really confuse Dtrace. But we did find one piece of malware on OS X, right? That's the problem, is that there's not a lot of stuff out there on OS X, but there was a simple DNS changer. So we wrote a script just to test it, if we can trace it and stop it from executing, understand what it's doing. So in a lot of cases, you're interested in the I/O that the malware will make. What functions does it open? What files does it open? What files does it change? Stuff like that. So again, the PT attached deny is the mechanism for avoiding Dtrace. There's this kernel. Let's see, right here is the URL for the kernel extension that disables PT attached deny by Landon Fuller. Okay, so here's another section to talk about kernel debugging on OS X. So you get something like this, right? This is Apple's blue screen of death, or Steve Jobs. We get it in 4 languages with the universal power symbol, so a nice fade and everything. I don't know about you guys, but if you ever use a Mac and sometimes it fades out to that media desktop thing. What is that called? I forget. It's like you can play music or view photos or something. But it has the same fade effect that this has, and it always freaks the crap out of me because I end up activating it somehow, and I think I just blue screen myself. So actually all the useful information gets put in this place called library logs panic reporter. So this is a dump of that file. So let me see if I can zoom in here and show you what's going on. Oh, it's totally different on my screen. Oh, there we go. So you can see this the CPU syntax or context there, right? We get first of all the kernel trap, page fault. This tells us what happened, right? So some sort of invalid memory access. Unfortunately, we don't have symbols on our stack trace because that's just the way it works when you don't have a remote debugger. But we can see these 3 functions, right, have the same address. They're in the same area. And this one's very different. Starts with 5C, this is 1.9. Also, it says up here, kernel trap at 5C31, blah, blah, blah. So that's the address where the bug really happened. Turns out the addresses are just signal handling stuff in the kernel. So this is the one we're really interested in. So you'll note this address here, CR204. I'm going to point this out on the next slide. You can't see this also here. They also note which kernel drivers are on the stack at the same time. So I just pulled this panic log out of my directory before doing this. So I haven't actually troubleshooted it, but this is like a real bug, right? So there's some keyspan drivers, a serial to USB connector, and it's got some driver to interface with it. So it tells me that in this kernel stack trace, although I don't have symbols, these are related kernel modules that have addresses in the stack trace. So you can see keyspan IOKit. The keyspan USA driver is loaded at this memory address through this memory address. That's where we saw the 5C earlier. So we know that we crashed within that kernel driver. So we can actually tell a lot just from this stack trace. Now, in the case of a page fault, the CR2 register tells us the address it tried to access. In this case, 4, right? Obviously bad. What we can do is map the runtime address where you crashed, this one right here, to an instruction address in the disassembly of the keyspan driver. So you go find the keyspan driver, open it in IDA, you do a little math down here to find out the correct offset, and you go look up what's happening at that instruction. So here it is. We see a move EAX plus, this one right here, EAX plus 4. So that's where our crash happened. You can see the value of EAX actually is 0. CR2 is what we tried to access, which is 4, so this all makes sense, right? Now we've pinpointed exactly where this crash happens, and we haven't even done any debugging yet. Now the problem is that now you need to do remote debugging because you have to try and reproduce this problem. We were hoping that with Dtrace, because it can trace kernel calls, you'd be able to somehow make this a lot easier. So we not need to set up a remote debugger. Let's just trace the kernel calls, look at the function parameters, and see what's happening. So I tried doing this, right? Let me run a kernel exploit against my machine that's going to DOS it and trace everything that happens in the kernel. Well, it turns out there's way too much stuff going on in the kernel. So you try and scope it down, but still, what's happening in the kernel that you're tracing never hits the disk before the DOS actually happens. So I haven't found a way to make this really useful yet. So, but there is a step in kernel exploit development where this still might be useful, and that's where you want to trace the data that you're sending to the application and see when it enters a particular function, what form does it have. So if you're tracing packets, you want to see that the packet parsing function gets called and the packet data looks like this. And then you change it a little and it looks like this. You change it a little and it changes in this way. So you can try and figure out what's happening at a higher level. But as soon as you actually DOS the machine, then you're screwed. So if you really want to do kernel debugging, what you have to do is set up a remote debugger, export symbols from your target machine, import them on your debugging host, set up some network magic so that they don't forget about each other, and then you can configure the target to enable kernel debugging, and it will look for the other host when something goes wrong. You can also do this with dumping kernel core dumps, so dump them to the remote host. There's a lot of documentation on this on Apple's site. I won't say a lot, but what you should look at really is this here, because they talk about the whole process of setting up the remote debugger. All right, so there's also new work being done to integrate probes, like higher level abstract probes into applications. So this means we can trace abstract actions like a page load, rather than the 10 million functions that get called during an HTML page load, or trace how long a DNS request happens. So a lot of this stuff is for performance monitoring, right? Because we have such complex Web 2.0 applications that we want to know where our bottlenecks are. But as reverse engineers, this can be interesting for us because we can hook things like the SQL parse, because we want to fuzz the application and then monitor what's happening on the database side. So for instance, we fuzz all our inputs and then we hook the database. So in this case, with MySQL, we might hook the dispatch command and then print out the argument. So this tells us exactly what SQL statement's being executed on the server. So then we can check our parsing routine to see, are they escaping quote marks? You know, how is it responding to our different inputs? So there's a lot more to be done in this area, right? Once we finish the programmatic debugger, there'll be a lot of fun things we can do, but also automated feedback and fuzzing stuff. If anybody wants to take a look at that, there's things like writing analysis libraries to better understand heap allocation, memory management, garbage collection. Also taking advantage of a lot of these JavaScript probes or MySQL probes or browser probes or whatever. So there's also probes in Python for when a Python function happens, or when an Objective-C function happens, or when a Ruby function happens. Because if you're just tracing the lower level functions, you're going to see all the stuff the VM's doing. And when you're debugging a Ruby app, usually you want to see what the Ruby functions are actually doing. They're also implementing new probe categories, things like the IP category, so you can trace packet receives and packet sends very easily, and TCP events too. That's all in the works right now. So a lot of what happens is this stuff gets put into Solaris 10 and then later adopted by the OS X developers. And of course, your own ideas. I'm sure you all have your own. I'd love to hear about them. So in conclusion, Dtrace gives you this ability to trace things at a very broad level, like across the whole OS, or trying to understand the behavior of something, or to zoom in and pinpoint a specific situation in which something happens. It is limited, though. There's only so many things you can do with a tracer. You really want to have a tracer, a good debugger, and a disassembler. So that's what we're aiming for here, is to get retrace, redbug, and IDA all together. All right. So that's my presentation. We're going to have redbug up soon on popopred.org, so check it. If it's not up, bug us. Yeah? We did some metrics with general tracing, like how much does Dtrace slow down an application in general, but we didn't do any metrics with comparing it to another heap smash detector. I wrote those stats down. It seems like in general, you'll see about a 63% decrease in performance or speed with a standard tracer, and with Dtrace, you see about a 10% drop. Of course, it depends on how many probes you instrument, but the performance is actually very good. In a lot of cases, when you try and use a tracer on anything besides Notepad, it's just ridiculous. It takes forever. And then when you try and use it like on a browser, for instance. But Dtrace lets you scope stuff, and it's much better performance in general. Anything else? Come on, guys. I know you want to ask questions. Okay, thanks.